A slinky spring can be used to show different types of waves. Figure 1a shows a longitudinal wave on a slinky spring. The wave travels from P to Q. Figure 1b shows a 120 millimeter ruler. Label a rarefaction in figure 1a. Remember, compressions are the high pressure, rarefactions are in between the compressions. So in the middle here is a rarefaction. You could have labelled it there or there. Give the wavelength of a longitudinal wave in the slinky spring. Now, it's much easier to see the centre of a compression than the centre of a rarefaction. In your exam, you have a ruler. It's much more tricky for me to do this. But a wavelength is easy to measure from the centre of a compression rather than the centre of a rarefaction. So that is a wavelength, the distance between one compression and the next. But that would be the same as the distance between one rarefaction and the next. So if I dot straight down, I make that 10. And here, the centre of that, I make that roughly 42. So the distance there is 42 minus 10 is 32 millimeters. And you could have had anything between 30 and 34 millimeters. Describe how a longitudinal wave is produced on a slinky spring. So what are you going to do? Remember, a longitudinal wave oscillates parallel to the direction in which it travels. So to get this slinky spring to oscillate, you're going to have to move it backwards and forwards, the key parallel to the direction in which the wave travels, not at right angles. So this is what you'd write. Moving the spring back and forth, parallel to the direction in which the wave travels. You could have said parallel to the spring, which would have given you full marks as well. Figure 2 shows a transverse wave travelling along a slinky. Which of the arrowed lines A, B, C or D shows the amplitude? Remember, amplitude is the maximum displacement from the undisturbed position, and that is your undisturbed position, so it is C. Figure 3 shows the emission spectra of 4 different gases, A, B, C and D. Neon has 2 spectral lines that are about 10 nanometers apart. These spectral lines are at the red end of the spectrum, which is the emission spectrum of neon. So towards the red end of the spectrum, you're looking for 2 lines about 10 nanometers apart. Well, those are 100 apart. These are about 50 apart. So can you see it must be these? So it is C. And just to check, D, those are easily about 20 to 30 apart. A diffraction grating is used to analyse the light from a star. Diffraction grating produces the spectrum of the light. Figure 4 shows the emission spectrum of elements P, Q, R and S, which can be found in the star. And this is the star's spectrum. Identify and justify which of the elements P, Q, R, S are found in the star spectrum in figure 1. You may add to figure 4 to support your answer. So I'm not sure that is needed in this case, but first of all, we've got to identify which of the elements are in this star. So it's making sure that you match up and see the lines. You can see R, all of the lines match up. So 1 would be R. You can see P, that line is not in the spectrum. So element P is not in the star. Q, that's in, that matches up as well. And so do those two. So R, Q, let's quickly check S. S clearly isn't because that line is not in the spectrum. So it's R and Q are the elements because their spectral lines are also in the star's spectrum. So those are your marks for 2 marks for identifying and that mark for justifying. Figure 5 shows rays of light passing through part of a diffraction grating. Diffraction grating produces a bright line on the screen. The distance travelled from the diffraction grating to the screen is different for each ray of light from the different slits. This is called path difference. Which path difference between the rays of light gives the bright line? So you want the light from all three of these to arrive in phase. So therefore, they must be a whole wavelength difference in path difference to arrive in phase. Or it could be a multiple of whole wavelengths. And the only one that works is D, one wavelength apart. Mobile phones should receive a signal when the user is in range of a transmitter. There are places where mobile phone signals cannot be received even when the user is in range of a transmitter. Figure 6 shows a mobile phone with no signal. Explain why a mobile phone might not receive a signal when in range of a transmitter. Now this is worth 2 marks, so you've got to have linked statements. And it could be any of quite a few. The first could be that there are no available channels or frequencies to connect because they're all being used or there's too much demand. The second one could be if you're in a built-up area, you could have large buildings which obscure or reduce the signal. It could be weather. If it's heavily raining, then that will absorb some of the microwaves so that you don't receive a good signal. The one that I would choose is that there are no frequencies available or channels available because they're being used up because demand is high. No available frequencies, channels, as all are being used due to high demand. For a mobile phone to receive a signal, the intensity must be above 9 times 10 to the minus 10 watts per meter squared. At a distance of 1.1 meters from the transmitter, the output signal has an intensity of 1.5 watts per meter squared. And the power given by the constant K is 1.8 watts. Calculate the maximum distance from the transmitter that a signal of intensity 9 times 10 to the minus 10 watts per meter squared can be received by a mobile phone. Give your answer in kilometers. So first thing I'll do under here is write kilometers so I don't forget when I put the answer down. Now again, they've given you the equation to use. This is about the inverse square law. And actually, they've given you too much information here because they've also told you what the constant is that they don't normally do. So I'm going to show you both ways of answering this question because normally they do not tell you what K is. The first thing to do is you need to rearrange the equation to find out what K is. So of course K is a constant which won't change in this scenario. So if we put this equation into a triangle, then K must go at the top, that constant, R squared must go underneath, so I goes here. And you can see that the constant is equal to I R squared, I times R squared. So if you know the intensity at a certain distance, then intensity times that distance squared will equal the new intensity at a different distance squared. So we can write I2 R2 squared equals I1 R1 squared. And that's the second distance away, this is the first distance away. And we want the distance. So I'm going to rearrange this for R2. So R2 squared is equal to I1 times I2 squared, and I2 is being divided. I2 is being multiplied here, so we need to take it to the other side by dividing. And now we've got to make sure we identify the right things. So this will be R1, and the intensity at R1 is I1. This is going to be the new intensity I2, and we want to find the distance R2. So putting the values in, we get 1.5 times by 1.1 squared divided by I2, which is 9 times 10 to the minus 10. And that gives you 2.0 times 10 to the 9. And remember, that is r squared. So r is going to equal the square root of that, which is equal to 44700 rounded up. And remember, that is in meters and we want it in kilometers. So that's going to be 44.7 kilometers. Now notice we haven't used this value at all, because that's the way we normally approach the inverse squared law questions, because we're not told the value of the constant. But in this case we are. So in the mark scheme they have this method, but actually there's a quicker method, because you don't need these values whatsoever to do this. And that's why I think it's a bit naughty putting this in like this. So rearranging the equation for r squared using the triangle, r squared is our constant divided by I. And our constant is 1.8, and our I is the new intensity, which is 9 times 10 to the minus 10. And that also gives you 2.0 times 10 to the 9, as it should do. Therefore, R2 is the square root of this, which again is equal to 44700 converted into kilometers is 44.7. Part C. Bluetooth and Wi-Fi use the same frequency bands. They use high frequency radio waves. Give one reason why Bluetooth signals do not interfere with Wi-Fi signals. Well, of course, the key word is they use frequency hopping. Now, you don't have to understand how that works, but it's used to make sure that Bluetooth signals of other Bluetooth devices don't interfere with Bluetooth devices and also with Wi-Fi, because they all use the same frequencies. State 2 useful applications of Bluetooth technology. So it needs applications, and you've got to think, what things do you use which you pair things remotely to? So of course the first one I can think of is wireless headphones. You could have wireless mouse, wireless keyboard. The other thing I'm going to do is mobile phone paired to car audio system. You could have had any of those. Light passes through an optical fibre. The optical fibre is made of glass. Calculate the critical angle for glass. So again, they've given us a refractive index, and they've also given us the equation rather than having to look at the back. So you don't have to rearrange the equation because it's already in the form sine of c. So the first mark would be putting the values in. So sine of c is 1 over 1.52, and that's equal to 0.658. It's more numbers than that, but I would quote it to 3 significant figures. Don't go down to 2. Now, of course, that's the sine of c. To find c, you've got to do the inverse of that, which is sine to the minus 1, 0.658. On your calculator, just look at where the sine button is and press shift sine, and that will give you sine to the minus 1. And that comes out as 41.1 degrees. If you're confident, you can do this in one step only. So you could, if you're confident, write sine of c equals 1 over 1.52, and then write c equals sine to the minus 1 of 1 over 1.52, which is equal to 41.1, by putting that into your calculator instead. Optical fibres used in cables can be covered in cladding. The cladding has a lower refractive index than the optical fibre. Figure 7a shows light passing through an optical fibre without cladding. Figure 7b shows light passing through an optical fibre with cladding. Explain one advantage of transmitting light through an optical fibre with cladding. Now the key thing is, if you're not sure, look at the pictures. They provide them to help you. You can see with cladding, only light with a larger angle is reflected. That would give you your first mark. And that's because the critical angle is increased with the cladding. So what's the advantage? Well, for the same length of optical fibre, the distance travelled by the light is much less, and not so much energy of the light is absorbed, and therefore it's not as attenuated, which means that you don't have to boost the signal as often. But this is only worth 2 marks. So what I would say is this: only large angles are reflected as critical angle increases, so less energy is absorbed as the light does not have to travel so far. Finally, this is a 6-mark question. Musical notes are sound waves. Plucking strings or forcing air through pipes can produce sound waves. Compare the types of wave formed on strings and formed in pipes when musical notes are produced. You may use diagrams to support your answer. Well, it's actually really important in this one to use diagrams, and it's also important for you to practice drawing standing waves for pipes and strings. And of course, if it says compare, you need to compare the similarities and the differences. So similarities are much easier. So first of all, the similarities. Remember that they're produced by oscillations, they're waves. They're produced when the string or air resonates. And they both produce standing waves. And you could also say that the harmonics they produce change the tone of the note. So those would be the maximum number of similarities. I'm going to bullet point those first, and then we'll look at the differences. Similarities. Both produce standing waves due to resonance. Both are produced by oscillations. The harmonics change the tone of the note. So next, looking at differences. So first I'll look at string instruments and then look at pipes. So for the string instruments, I would draw the first harmonic, the second harmonic and the third harmonic and explain how much of a wavelength is and what are the frequencies. Also remember that we can adjust the pitch of a string by changing its length, by changing the tension on the string, and also by changing the thickness, which changes the mass per unit length. So the first resonance point is your first harmonic, and I'd also draw the nodes and antinodes on and label that the first harmonic. I'd also put F0 to show that that's my first frequency, so I can show what happens to the frequency. I'm also going to show that I understand that the length of that is half a wavelength. So the next one, I've got, keeping the same size, I've got a node in the middle. I've got 2 loops now. And the length of that is going to be a whole wavelength this time. And this is the second harmonic. And it's twice the fundamental frequency. So already the examiner can see I understand that totally. And I'm going to do the third harmonic now. So the third harmonic has 3 loops. Do practice doing these. It really helps. I'm very close to the bottom there. I can't finish that off because it's at the end of my tablet. But that length there is 1.5 of a wavelength. Each loop is half a wavelength. Node there and node there. We don't have to label the rest, but this will be the third harmonic, which is 3 times f0. So I can round this up by saying produces even and odd harmonics. The pitch can be changed by changing the length, tension and thickness. Most students would say, but that is changing the mass per unit length. So what about pipes? Of course, unlike strings, pipes have 2 different types. You can have an open pipe or a closed pipe. 2 types, open and closed. So I'm going to try here and divide this up here to show you don't have to write a huge amount. So first of all, I'm going to start with closed. So with a closed pipe, remember you've got a node at one end and an antinode at the other. So that is only 1/4 of a wavelength. And if we make that our first harmonic, I'll call that f0. The next one up, and this is where you need to practice it, the next one up is not the second harmonic, but the third harmonic, because if you put an antinode there, then you've got to have 2 nodes here to make that waveform the next resonant frequency, and that will be 3/4 of a wavelength. A half plus 1/4, 3/4 of a wavelength. So this won't be your second harmonic, this will be the third harmonic, and that's going to be 3 times f0. So that's your closed pipe. It only produces odd harmonics. So closed pipe instruments do sound quite different from open pipe instruments because the upper harmonics change the tone of the note. So what about an open pipe? Well, the first one, you don't have to say there's an antinode at both ends because you're drawing it on. So there'll be a node in the middle, and that is 1/4 plus another 1/4, so that is half a wavelength. So that's half a wavelength, just like a string instrument. So first harmonic, and write f0 again because that is the first frequency. Then I'm going to just draw one more to show the difference between the two. So this is an antinode. I've got to have a node here, an antinode there. Again, practicing it lots before your exam really helps by being able to sketch these. So that is now a whole wavelength. That's a half plus 2/4. So that is a whole wavelength. So that is double that frequency. So that is the second harmonic. So 2 times f0. I'm not going to do the third because we can already see that this produces all harmonics like the string instruments. And finally, I could just put here, for both of them, pitch is only changed by the length or the pressure. So you can clearly see that actually knowing these diagrams and being able to draw this helps enormously to put that across without having to write a huge amount.